Hello everyone, in this video we are going to discuss first order first degree differential equations which are reducible to homogeneous. So let's first have a look at the general form of such equations. Such equations look like dy by dx equal to a linear in x and y above and another linear in x and y below. Now we see that we have discussed such equations in reducible to separable category also when the coefficients of x and y were proportional above and below. So whenever we have a1 by b1, the coefficient of x above and below, this ratio, if that is the same as the coefficient of y above is to coefficient of y below, then such equations can always be reduced to separable category, which we have already discussed in one of the previous videos. So such equations are manageable using reducible to separable procedure. Now what if this ratio is not the same as the other ratio? In this situation, we can do something to make it homogeneous, and the procedure of doing that is what we intend to discuss in this video. So the general class of equations that we are discussing in this head are going to look like dy by dx equal to a linear in x and y above and a linear in x and y below, with a constraint that the ratio of x above and below is not going to be the same as the ratio of y above and below. Such equations cannot be reduced to separable, but they can be reduced to homogeneous through a process which we will be learning through some examples here. So let's look at the first example. Suppose the question is to solve the differential equation which looks like this. Let's say x minus 2y plus 1 dx plus maybe 4x minus 3y minus 6 dy equal to 0. Or we can say dy by dx is the same as x minus 2y plus 1 upon 4x minus 3y minus 6 with a negative sign. So let's see and try to compare it with the general format. It's a linear in x and y above and a linear in x and y below, but the ratio of x above and below is 1 by 4 and the ratio of x above and below, y above and below is minus 2 by 3. So they are not the same. We cannot reduce it to separable, but we can reduce it to homogeneous by introducing two new variables. Let's introduce two new variables, say capital X and capital Y, in such a way that capital X is a translate of the earlier x. It's x minus some constant, say h, and capital Y is y minus some constant, say k, where these h and k will be determined later on, will be chosen suitably later on. So suppose x is a translate of x, small x, capital Y is a translate of small y, then obviously since they are just translates, so the old and new derivatives have a direct relationship. Dy by dx, the old derivative which was small dy by dx, is now going to be the same as capital dy by dx, because x is just a linear translate of small x. So d of capital X is same as d of small x and d of capital Y is same as dy by dy. So this is effectively giving us dy by dx is the same as dy by dx. The old dy by dx matches the new dy by dx. Now when we substitute this new variable capital X capital Y in the given equation, then this equation can be rewritten as, in the new setup, in the capital setting, we can write dy by dx as dy by dx only, but here we'll have a change. Our small x is capital X plus h, so we replace it here like this. Our small y is y plus k, so that makes it minus 2y minus 2k above, and there was a plus 1 attached to it. So that's what happens to the numerator in the new variables, which are capital X and capital Y. Now let's look at the denominator. It takes the shape 4 times small x, you can see from here, is capital X plus h. So this becomes 4x plus 4h, and here it's a minus 3 of y. So minus 3 capital Y minus 3k, and then you have a minus 6. So that's the new denominator and that's the new numerator in the capital variables which we have introduced. Now if we simplify a little more, then we can see that dy by dx can take this form minus x plus 2y, and rest of it is a constant. The constant above is minus h, and then we have a plus 2k and minus 1, and then here we have 4x minus 3y as the non-constant term, and the effective constant in the denominator takes the shape 4h minus 3k minus 6. Now here comes the stage when you are going to choose your h and k. So we choose h and k in such a manner that the overall constant above, which is this expression, and the overall constant below vanishes. If we do that, if there is no constant above, there is no constant below, then you can see that it's a homogeneous expression which is left out on the right hand side. Dy by dx becomes a homogeneous expression in capital X and capital Y if we choose these two expressions to be 0. So if we do that, we put this restriction on h and k, that h and k should be chosen in such a way that minus h plus 2k minus 1 is 0, or I can write h minus 2k plus 1 is 0 taking negative common, and 4h minus 3k minus 6 is 0. Then you can see that this is a system of two equations in two unknowns h and k which can be easily solved. We can see that when we solve the system, multiply by 4 and subtract and all that stuff. So h comes out to be 3 and k comes out to be 2 after solving the system. Now with this choice of h and k, you can see that this choice of h and k leads to the expression, the overall constant above as 0 and the overall constant below also as 0, effectively leading to dy by dx being equal to, we are left with what? We are left with minus x plus 2y above and 4x minus 3y, with h being equal to 3 and k equal to 2. So this choice of h and k leads us to a new equation which happens to be homogeneous in capital X and capital Y. So we know how to solve homogeneous. It's the usual way, which is homogeneous in x and y. The new equation has turned out to be homogeneous in x and y, the new variables which we had introduced as translates of the old variables. H and k are suitably chosen so that the overall constant above and below vanishes. Now how do we solve the homogeneous equations? We do it the normal way. We take y by x as v, then dy by dx is v plus x dv by dx. This is all discussed in the previous video, how to solve homogeneous equations. So we do it the normal way. Left hand side, the derivative takes the value v plus x dv by dx, and the right hand side takes the shape minus 1 plus 2v upon 4 minus 3v. Now we can see that it's a separable equation in v and x. Now we take v to the other side, we solve it the usual way we have been doing homogeneous equations. After the substitution y by x equal to v, homogeneous becomes separable. So that's the approach that we are following here also. So we can see that effectively when we simplify, it's x dv by dx is minus 1 plus 2v minus 4v plus 3v square here, and then we have a minus 3v plus 4 in the denominator. So this simplifies to the following. So we can have x dv by dx here written as it is. This is 3v square minus 2v minus 1 upon 4 minus 3v, which comes here. Now taking things to the other side, we can say 3v minus 4 upon 3v square minus 2v minus 1 of dv is the same as minus 1 by x dx. Integrating both the sides, this is a usual log integral. The answer to the integral of 1 by x is log of mod x, and here this is a linear above and a quadratic below. The usual integration techniques, partial fractions and so on, are going to give us this answer. It's very easy to verify this integration using the usual techniques of integration. There will be a 3 attached to this, yeah, and then we have a log happening here. So it's the usual partial fraction technique of dealing with such integrals, which leads to this answer. And on the right, it's very easy. Since everywhere logs are involved, we take the constant also as log c. which helps us to simplify it more, and we can write it, we can take 2 common, we can take 2 with this to make it 3v square minus 2v minus 1, then you have a minus 3 log of 3v minus 3 upon 3v plus 1, and then we take the 2 here because we are multiplying throughout with 2 to take the steps ahead and make the solution a little presentable. So 2 goes here also if we want, otherwise we can replace this by a new constant name, let's say capital C or something, and then combining the logs we can see that it takes the form log of 3v plus 1 to the power 5. After all the simplification and cutting it out, it takes this shape. C1 to the power 4 can be written as C1 to power 4 only. Here we get a x to power 4, and then finally we can remove logs and get the answer as x to power 4. 3v plus 1 to the power 5 is cv minus 1. This is usual integration, reducing to homogeneous, then putting y by x as v, then taking everything involving v on one side and everything involving x on other side, using partial fractions and so on. Now in the end this is what the answer looks like, but remember v stood for y by x, so this is the step that we should not forget, because v was something introduced by us and y and x also were introduced by us. The original variables were small x and small y. So do not forget to replace the value of small x and small y. If you go back, you see small x happens to be capital X plus h, and h is something that we found out during the procedure. So capital X is x, you can see from here, x minus h. Capital X is x minus h. H has taken the value 3. So x minus 3 comes here, and similarly capital Y is y minus 2. This implies that this is the solution where capital X has this value x minus 3 and capital Y is y minus 2. If we want, we can substitute it here and simplify it a little more to make the answer look exactly in terms of x and y. Otherwise this can be left here also. So that's how we deal with equations which are reducible to homogeneous. It's a lengthy technique. There are other better ways of dealing with such equations. See, when we do any kind of first degree differential equations, do not expect a unique way of tackling one particular differential equation. Since there are multiple ways, the given differential equation may be following under certain heads which are like exact, maybe separable, maybe reducible to separable, or homogeneous. So you have to choose the best type which suits you calculation wise and the level of difficulty which is involved in any kind of procedure. So we have to use our own wisdom to decide what technique we'll be following. So this happens to be the worst technique if we talk about the length of the solution, because it is involving a lot of substitution. You are first introducing your capital X and capital Y, then you are making it homogeneous, and then you are doing one more substitution. You are introducing v, which is y by x, and then making it separable, then solving in terms of v, putting v as y by x, and then y by x are also something which we had introduced, so they are to be put back in terms of small x and small x. So it's a very lengthy procedure and happens to be the worst procedure calculation wise. The length of the solution is a little heavy on our heads, but yes, it is if it is the last resort, your given equation is not falling in any of the categories that we are discussing, then obviously you will be required to use this category. So one should know how to reduce equations which are not homogeneous. They look like linear in x and y above, linear in x and y below, with constants being non-proportional, and this is one way which you may be resorting to if required. So one should know how to handle reducible to homogeneous category also. So this was all about this video. In the next video we are going to learn the next type of first order first degree equation, which is linear differential equations. So that's all for now. Thank you for watching. Stay tuned.